In this video, I will be discussing about areas between two curves. Consider two continuous functions f of x and g of x at some closed interval from a to b. Now, suppose this is the graph of our f function. So, this is the curve defined by the function f of x. And suppose we have another function, say this function that is defined to be the graph of the g function. Now, our goal is to find the area bounded by these two curves. So, to find the area between these two curves, let us find the intersection points. And suppose this point has x coordinate of a and this point has an x coordinate of b. So we can find the coordinates of this point. So this is a, f of a, because if you substitute a to the f function, this is this point. And also this point is having coordinates of b, f of b here. However, we can also find this point by substituting a to our g function, this graph here. So this is a, g of a. It will give you the same value as the f of a. And so with this one, this can be found by substituting b to our g function. So this point has coordinates of b, g of b. And in order to find the area of this shaded region, we need to slice the whole area. So slicing the area from a to b vertically, we can pick one slice here. So suppose this is our one arbitrary slice. This slice is having a thickness of delta x, and the length of this arbitrary slice is the upper boundary of this slice, which is the y of this curve, which is the f. So this is f of x minus the y of this curve, which is the g of x. So therefore, we can find the area of this shaded region if we will add up all the slices that covers the whole shaded region. And this can be written mathematically as a approximately equal to the sum of all the slices, and the arbitrary slice is represented by f of x sub I minus the g of x sub I here. Now take note that this is only the height of this arbitrary slice. And to find the area, we need to multiply this height by its width, which is delta x. Now remember that there are how many slices? There are n slices. So if you're going to slice this one n times, this is the expression mathematically. Now take note that this is only an approximation of the area. Why? Because if you take a consideration of this arbitrary slice, this side is not a straight line, and so with this one. So there is a discrepancy of the area. So there is what we call an excess area at that part. So that is why this is only an approximation. But this approximation becomes perfect when this delta x goes to 0. And when this delta x goes to 0, it goes to 0 when n goes to infinity. In other words, if you slice this shaded region into infinitely many slices, then the discrepancy will be almost nothing. So the excess area will eventually disappear. So our area can be written as the sum of all rectangular strips, this vertical strip here, which is represented by its height, so f of x sub I, minus the g of x sub I there, times its thickness, which is delta x. And there are how many slices? There are actually infinitely many slices. So we write here the limit of this sum as n goes to infinity. And you notice that this area is an exact area for this shaded region. Also, we notice that this is the limit of a Riemann sum. And then we recognize that this is the same as the integral. So it's the integration of all the slices from A to B, because you are slicing it infinitely many from A to B vertically. And what is the length of every slice? It is defined to be f of x minus g of x times its thickness of d of x, or dx. So therefore, this is our formula in finding the area of this shaded region. Now, what if the given function is not a function of x, but a function of y? So, suppose this is the graph of the function, which is a function of y, say h of y. And there is also another function, say this one, which is defined by the equation x, which is equal to the g of y. Now take note that the functions are not in terms of x, but in terms of y. And our goal is to find this shaded region. Now, to find this shaded region, we need to find these 2 points of intersections. And these 2 points of intersections can be solved by solving simultaneously these 2 equations. And suppose this point of intersection is having an x-coordinate of, say, h of c, then it has a y-coordinate of c. So this is the y-coordinate of that point. And also this point is having an x-coordinate of h of d. So the y-coordinate is d here. But this point can be obtained by substituting also c to the g function. So this is g of c, c. And so with this one, g of d, d, using this function g. Because at this point, the h and the g are the same here when the y is d. And the idea is to slice this one horizontally, starting from D here to C. So we are slicing the y. So that's why our slice is in horizontal position. And suppose this is the representation of an arbitrary slice here. Now this arbitrary slice, it has a thickness of delta y, but the length of this arbitrary slice is obtained by subtracting this x function, which is the h of y, minus the g function, g of y here. So mathematically, we can represent the area by adding all the slices here. So this is the sum of all slices, which is the h of y sub I minus the g of y sub I. Now take note that this is only the length of the slice times its thickness, which is delta y. And there are how many slices? There are n slices, starting from the lowest slice up to the highest slice there. Now you notice that this area is only an approximation of the shaded region. Why? Because every slice has a side here that is a straight line. But take note that this is not straight, it is a curve. So there is a little discrepancy of the area. And that discrepancy, sometimes it's greater than the actual area, sometimes it is lower than the actual area. Now, suppose that it's greater than the actual area. Then therefore, there is what we call an excess area. So that is why that the area is only approximately computed by this formula. However, this approximation becomes perfect when you will slice the whole shaded region into infinitely many slices. So you will slice it infinitely many, not only 100, thousands, not only 1,000,000, billions, but infinitely many. So when that happens, the approximation becomes perfect at this time, because this is the sum of all the slices, which is represented by h of y sub I minus the g of y sub I. So this is the length times its width of delta y. And there are how many slices? There are actually infinitely many slices at this time. Why it becomes perfect? Because the excess area, the discrepancy, will eventually disappear, because every slice becomes thinner and thinner, and therefore you cannot notice the difference of the actual area and this horizontal area element. Now we notice that this is the limit of a Riemann sum, and we know that this is equal to the integral. So it is the sum of all the slices from D to C here of h of y minus the g of y times d of y. Then therefore, this is our formula for the shaded region if we slice the shaded region horizontally at this time. Now let's apply the formulas that we have derived a while ago. Find the area bounded by the curves y equals x cubed and y equals 4 minus 3x squared. Now we know that the graph of this cubic function is this one here, and we know that this is a parabola opening downward with the vertex at 0, 4. So since the vertex is at the point 0, 4 and it's opening downward, so we can sketch the graph of this parabola here. And the area that we want to find is this one here. So let's label the function of this curve y, which is equal to 4 minus 3x squared. And also this one has a definition of y equals x cubed. And to find the area of the shaded region, let us find the points of intersection. And to find these points of intersection is to solve simultaneously these two equations. So solving these two equations, we have our equation 1, which is y equals x cubed, and our second equation, which is y equals 4 minus 3x squared. Then we say that the two equations, the two expressions at the right are equal because they are equated to the same variable y. So this can be written as x cubed, which is equal to 4 minus 3x squared. Now, moving all these terms to the left side of the equation, we have x cubed plus 3x squared minus 4, and the whole thing is equated to 0. And factoring this cubic expression, we know that this is equal to x minus 1 times x squared plus 4x plus 4 there. Since we can divide this one by x minus 1 using the synthetic division. So 1, 3, 0, and negative 4. Because if you divide this one by 1, we have 1, and 1 times 1 is 1, so this is 4. 4 times 1 is 4, so this is 4. 4 times 1 is 4. And therefore, the remainder is 0. So that is why we have a root of 1. So one of the factor is x minus 1, and the quotient is having these coefficients. So x squared plus 4x plus 4. So that's why we have this quadratic expression. But this one can still be factored out. So this is x minus 1 times x plus 2 quantity squared, because we know that this is a perfect square trinomial. And equating these factors to 0, we have the roots of 1 and negative 2 there. So if our x is negative 2, then our y, we know if you substitute this x to the first equation, we have our y, which is negative 8, because negative 2 to the power of 3 is negative 8. And if our x is equal to 1, our y is also 1, because 1 cubed is 1. So therefore, our points of intersections are negative 2 and negative 8. So with this one, having coordinates of 1, 1. So we know that the coordinates of this point of intersection is negative 2, negative 8. And this one is having coordinates of 1, 1. Now, looking at this shaded region, it is very easy to find the area when we slice it vertically. Why? Because if we draw here a representative of a slice, when you slice it infinitely many, we notice that the upper boundary of all the slices are found in this curve. And also the lower boundary of this slice is found in this curve also. And wherever is the slice, it has the same boundaries. And why is it that this is not easy when you slice it horizontally? Because when you slice it horizontally and the slice happens at the lower portion, the left boundary is this curve and the right boundary is this curve, y equals x cubed. However, when your slice happens to be at this point, the left and the right boundary happens to be in the same curve. So they don't have constant boundaries for all the slices. Hence, it is easier to slice the whole region vertically. And remember that the thickness of this slice is our dx. And the length of this slice is the difference of their boundaries. And we know that this is the upper boundary and this is also the lower boundary. So we say that the area is equal to the integral of the upper boundary, which is 4 minus 3x squared there, minus the lower boundary, which is x cubed. Now remember that this is only the length of every slice, and it has a thickness of dx. Slicing it starting from negative 2 to 1. So that's the limits of our integration. Look at this. we are slicing the x. So let us look at the x coordinates of these points. So we are slicing from -2 to 1. Now at this time, we can simplify our answer by removing the parenthesis at this time. So this is 4 minus 3x squared minus x cubed dx. And finding the integral of this cubic expression is 4x, because the integral of 4 is 4x, and the integral of this 3x squared is 3x cubed over 3 minus x to the power 4 over 4, and this will be evaluated from the limits, which are -2 to 1. So we have the area, which is equal to 4 times the upper limit of 1. So 4 times 1 minus 1 cubed, because this 3 and this 3 cancels each other. And we have minus 1 to the power of 4 over 4. And this will be subtracted by this expression when substituting this -2. So we have 4 times the -2 minus -2 to the power 3 minus -2 to the power of 4 over 4 here. So we have the area, which is equal to 4 minus 1 minus 1/4 plus 8, because this is -8, and because we have this negative here, therefore the result is positive. And this is -8, so negative of the -8 is +8, but we have here a negative, so this is -8. Also, this one is +16 over 4, which is 4, but this is -4. With the negative outside, this becomes +4 here. So simplifying further, we have 4 plus 4 is 8. So 8 minus 1 is 7. And this is subtracted by 1/4, because 8 minus 8 cancels each other. So therefore, the whole thing, if you combine these two terms, you will have a common denominator of 4. So this is 28 minus 1. So the whole area is 27 over 4 square units. So this is the area of this shaded region. Now, let's proceed to our example number 2. Determine the area of the region bounded by the parabola y squared is equal to 2x minus 2 and the line y equals x minus 5. Now, we know that this is a parabola opening to the right whose vertex is at the point 1, 0. So it has the vertex at this point, at the point 1, 0. And it is opening to the right here. But the graph of this is a straight line but having a positive slope. So it is sloping upward. And the graph intersects in this parabola from this point here. So it has a points of intersection. Now let us label that this is having an equation of y squared, which is equal to 2x minus 2. And this one is having equation of y, which is equal to x minus 5. And our goal is to find the area of this shaded region, because this is the area enclosed by these two curves. And since we have two functions here, we'll represent this one as our y sub 1 and this one as our y sub 2. And if you slice this shaded region at this point here, we got a representative of the slices whose upper boundary is the y of this curve, and the lower boundary of this slice is also on the y of this curve. But this one is negative because this is below the x-axis. So therefore, to find the length of this slice is y sub 1 minus the negative of y sub 1, because it has upper boundaries and lower boundaries in the same curve here. However, if you happen to have a slice at this portion, it has a different set of boundaries because the upper boundary is in this curve, but the lower boundary is at this straight line. So therefore, to find the length of this slice, this is y sub 1 minus y sub 2. So it's the upper boundary, which is from this curve y sub 1, this is y sub 1 minus y sub 2, because this is the upper boundary from this curve y sub 1 and having a lower boundary from this straight line y sub 2. So therefore, we need to partition the whole region into two from this point of intersection. And we say that this is our area 1 and at this subregion area 2. So therefore, the whole area is obtained by adding the two regions here. So area is equal to the integral of y sub 1 plus y sub 1, because y sub 1 minus the negative y sub 1 is y sub 1 plus y sub 1 here, and it has a thickness of dx in this slice. So dx there, and this is added to the integral of this subregion, the integration of all the slices, and the length of the slice is y sub 1 minus y sub 2, and of course it has the same thickness of dx here because this one having a thickness of dx, but we don't know the limits of integration yet because we don't know the points of intersection. So to solve for this point of intersection, we need to solve simultaneously the two equations. So we have equation 1, which is y sub 1 quantity squared, which is equal to 2x minus 2. And our second equation is the equation for the straight line, which is y equals x minus 5. And how do we solve it simultaneously? We just substitute equation 2 to equation 1. So we have y sub 2, this one, which is from here. We have x, because the value is x minus 5. So x minus 5 quantity squared, you substitute it here, which is equal to 2x minus 2. And squaring this binomial, we have x squared minus 10x plus 25 minus 2x plus 2 is equal to 0 if you move these two terms to the left. And therefore, our quadratic equation is x squared minus 12x plus 27, because when you add negative 10x to negative 2x, we have negative 12x, and 25 plus 2 is 27. But we can factor this quadratic into x minus 9 times x minus 3. And you can check this factoring by multiplying x to x, we have x squared here. And multiplying negative 9 and negative 3, we have positive 27. And to get the middle term, we multiply negative 9x and this one, which is negative 3x, and add them. So negative 9x plus the negative 3x, we have negative 12x. And equating these factors to 0, we have the roots of the equation, which are 3 and 9. Thus, the points of intersection is 3. When you substitute 3 to any of the equation, say this one, 3 minus 5 is negative 2. And the other one is when x is 9. So 9 minus 5 is 4. So we have coordinates of 9, 4. Then therefore, this one is 3, negative 2. This point of intersection. And this one is having coordinates of 9, 4 here. And now that we have the points of intersection together with this vertex of the parabola, then we would know also the limits of integration. Because in this region 1 here, you will be slicing from 1 to 3. So look at the x-coordinate of this point, that is 1 to 3. So our limits of integration in region 1 is 1 to 3. However, the limits of integration of this region 2, which is this one here, you will be slicing from 3 to 9. So this is from 3 to 9. Now, substituting our values of function, we have area which is equal to the integral from 1 to 3 of 2y sub 1 dx plus this integral from 3 to 9 of our y sub 1. And our y sub 1 is this one here. So solving for the y sub 1, we have y sub 1 which is equal to the square root of 2x minus 2 if you take square roots of both sides in order to solve for y. So we have the square root of 2x minus 2 minus y sub 2, which is x minus 5 there. So factoring this constant of 2 outside the integral symbol, we have 2 times the integral from 1 to 3 of our y sub 1 dx. And also, this is added to the integral from 3 to 9 of this one. Let us separate these expressions here. Say this is 2x minus 2 to the power 1/2 dx. And because this is a minus, we have minus the integral from 3 to 9. We will be using the same limits of integration for x minus 5 dx here. Now, substituting our y sub 1 here, we have area which is equal to 2 times the integral from 1 to 3 of 2x minus 2 to the power 1/2 dx plus the integral from 3 to 9 of our 2x minus 2 to the power 1/2 dx minus the integral from 3 to 9 of x minus 5 dx here. Now, we can use the dummy variable by substitution. We have u which is equal to 2x minus 2. And if you get the differential of u, we have 2 dx. But we don't have the 2 dx here, only dx. So we can divide both sides of the equation by 2. So we have dx. So by substitution, we have area which is equal to 2 times the integral of u to the power 1/2 times the value of dx, which is du over 2 here. So instead of writing dx, we will write du over 2. But the limits of integration is u of 1 to u of 3 because we are changing the variable to u, plus the integral of u of 3 to the u of 9 of u to the power 1/2. Instead of writing 2x minus 2, we will write its representation, which is u. And instead of writing dx, we will write du over 2 minus the integral of x minus 5, and the integral of x is x squared over 2 minus the integral of 5, which is 5x evaluated from 3 to 9. So we have the area, which is equal to 2 over 2. When you factor out this denominator outside this integral symbol, we have the integral of u to the power 1/2. So we have u to the power 3/2 over 3 over 2. And this will be evaluated from u of 1 to the u of 3, added to 1/2 times the integral of u to the power 1/2, which is u to the power 3/2 over 3/2. And this will be evaluated from u of 3 to the u of 9, minus this one, which is 9 squared over 2 minus 5 times 9. And this will be subtracted by 3 squared over 2 minus 5 times 3 there. So simplifying our answer, we have the reciprocal of 3/2, which is 2/3 times this u to the power 3/2, but our u is 2x minus 2, and this will be raised to the exponent 3/2 evaluated from 1 to 3, plus 1/2 times the reciprocal of this, which is 2/3 times this u to the power 3/2, but our u is 2x minus 2, and this will be raised to the exponent of 3/2 evaluated from 3 to 9, and this will be subtracted by 81 over 2 minus 45, but I can express 45 as 90 over 2 so that they will have the same denominator, minus 9/2, and this is minus 15, but because we have a negative outside the parenthesis, this will become positive 15, and positive 15 can be written as 30 over 2 there. So we have area which is equal to 2/3 times the quantity of 2 times 3, which is 6, and 6 minus 2 is 4, and the square root of 4 is 2, and 2 cubed is 8, so that is 8. And when we substitute this one here, we have 2 times 1 is 2, and 2 minus 2 is 0, and 0 to the power 3/2 is still 0, and this will be added to 1/3 because this 2 and this 2 cancels each other, and we have this 9 here. So we have 2 times 9 is 18 minus 2 is 16, and the square root of 16 is 4. 4 cubed is 64, minus this 3 when multiplied to 2 is 6, and 6 minus 2 is 4, and the square root of 4 is 2. 2 cubed is 8. So this is minus 8 minus this quantity here. And we know that this 81 added to 30 is 111 over 2. And minus 90 over 2 minus 9/2 is minus 99 over 2. So we have this area which is equal to 16 over 3, because 2 times 8 is 16, plus this 64 minus 8, which is equal to 56, and 56 over 3 minus this 111 over 2 minus 99 over 2 is 12 over 2, and 12 over 2 is 6. So we have here 72 over 3 minus 6. And 72 over 3 is 24. And 24 minus 6 is equal to 18 square units. So therefore, this is the area of this shaded region. Now, at this time, I'd like to solve the same problem using another method. So I will draw the parabola that is opening to the right here, that is intersected by this straight line at the points 3, -2, and this point 9, 4, with the vertex at the point 1, 0. Now take note that we want to find this region, area of this region. Now let us label this one by its function. So this is y sub 1 squared, which is equal to 2x minus 2. And this one also is our second function, y sub 2, which is equal to x minus 5. But at this time, instead of slicing it vertically, we will slice it horizontally. Why? Because this region is a region of type 2. Why? Because when you slice it horizontally, all the slices are having the same boundaries here. Notice that wherever is your slice in the region, your left boundary is on this curve and the right boundary is on this line here. Thus, we observe that every slice is having the same boundaries. The left boundary on this parabola and the right boundary on this line. So we can therefore find the length of this horizontal strip, that this is the x of this function. So this is x sub 2 minus the x of this function. So the x boundary of this line minus the x boundary from this curve. So therefore, we need to solve for x for this line. And x is equal to y plus 5, which is equal to our x. And since this is y sub 2, so this is x sub 2 here. And also, this one, you can solve for x by moving this -2 to the left. So we have y squared plus 2, and dividing both sides of the equation by 2 is the value of our x sub 1. So therefore, we can write our area as the integral. So the integration of all the slices from the bottom to the top, whose length is x sub 2 minus x sub 1 with the thickness of dy, and slicing it from this point up to this point. Because we are slicing the y, we will be looking at the y coordinates. So from -2 to 4 here. And I'd like to remind you that you must be careful with the limits of integration, because at this time you are slicing horizontally. So therefore, you slice starting from the y of this point, which is -2, up to the y of this point, which is 4. That's why our limits of integration is from -2 to 4. And substituting our function, we have the integral of -2 to 4 of our x sub 2, which is y plus 5, minus our x sub 1, the x coordinate of this curve, the x function of this curve, which is this one here. So this is minus y squared plus 2 over 2. And this will be integrated with respect to y. And at this time, we need to separate these two terms here. So this is the integral from -2 to 4 of y plus 5 dy, minus the integral from -2 to 4 of y squared plus 2 over 2 dy. So we have the area, which is the integral from negative 2 to 4 of y plus 5 dy minus 1/2, because we need to factor out this denominator here outside the integral symbol. So this is minus 1/2 times the integral from negative 2 to 4 of y squared plus 2 dy. And integrating this expression here, the integral is y squared over 2 plus 5y evaluated from negative 2 to 4. And this will be subtracted by 1/2 times the integral of y squared, which is y cubed over 3 plus the integral of 2, which is 2y from negative 2 to 4. Therefore, our area is equal to this expression. When substituting this 4, we have 4 squared over 2 plus 5 times 4 minus the quantity of y, which is negative 2. So this is negative 2 squared over 2 plus 5 times the negative 2 there, minus 1/2 of the quantity when you substitute this 4 here. So this is 4 cubed over 3 plus 2 times 4 minus this negative 2 to the power of 3. So this is added to 2 times the negative 2 there. So we have the area, which is equal to 16 over 2, which is 8 plus 20, and this is 4 over 2, which is 2. So this is minus 2. So minus of the minus 10, which is positive 10. And this will be subtracted by this 64 over 3. So we have 64 over 3 plus 8. And this is negative 8 over 3, but we have a negative here, so this is positive 8 over 3, and minus the negative 4, so we have positive 4. So we have 28 plus 8, and 28 plus 8 is 36, minus 1/2 times this quantity. So 64 plus 8 is 72. And 72 divided by 3 is 24. So 24 plus 8 is 32. 32 plus 4 is 36. Therefore, our area is equal to 36 minus 1/2 of 36, which is 18. And 36 minus 18 is 18 square units. So therefore, our area is 18 square units for this shaded region. And you can check that our answer is the same answer when we solve the same problem, but in the first method, we slice it vertically. And in this solution, we slice the whole region horizontally. But the amazing result tells us that we have the same result, no matter whether you slice it vertically or you slice it horizontally. And one thing for sure is that one is a little bit longer than the other, and your experience and practice will dictate which method is shorter and which method is longer. And that's it. If you learned something today, please check out my channel for more videos like this and click subscribe. Click the notification bell below so you'll get notified whenever I'll be posting a new video. Don't forget to like this video to show your support. And always remember to math your way up. Thank you.